Hello AAT. Today we are going to solve systems of equations algebraically. That is our goal for today. And in order to solve algebraically, we are going to solve these systems using substitution and elimination. Let's start by solving this first system using substitution. In order to use substitution, we are going to need to isolate a variable. So that means get one of the variables by itself on one side of the equal sign. So if I look at my two equations and how they're set up, I'm going to use the first equation in order to isolate the y, because the y has a 1 as its coefficient. That's going to be the easiest for me to isolate. So I'm going to take my first equation and rewrite it. So therefore I can subtract 3x from the left side and the right side, so I am left with y is equal to negative 3x plus 7. Now that y is isolated, I can see that the left side, y, is equal to the right side, which is negative 3x plus 7. If I take this whole right-hand side, negative 3x plus 7, I can substitute this in for y into my second equation, 4x plus 2y equals 16. So wherever I've previously had a y, I'm now going to substitute in negative 3x plus 7. So 4x plus 2 times the quantity of negative 3x plus 7 is equal to 16. As you can see, everything else stays the same. The 4x plus 2 stays the same, and the 16 stays the same. The only thing I did was replace y for this quantity. Now let's combine like terms, distributive property first. So I have 4x minus 6x plus 14 is equal to 16. 4x and 6x are like terms, which combine to be negative 2x plus 14 is equal to 16. I'm going to zero out 3 from the left, subtract 3 from the right, so I am left with negative 2x is equal to positive 2. And finally, I'm going to 1 out negative 2 from the left, divide by negative 2 on the right, so x is equal to negative 1. So now that I have x, how do I get y? I'm going to take my quantity for x and substitute it back in to x in one of my original equations. It doesn't matter which equation you plug it into. I'm going to choose the first because, again, that first equation in the y has a coefficient of 1. That leads for less work later. So 3 times where x was, I plug in a negative 1 plus y is equal to 7. 3 times negative 1 is negative 3 plus 7 is equal to 7. I add 3 on the left-hand side and on the right-hand side, so finally y is equal to positive 10. My solution to this equation can be written as an ordered pair, and my solution is going to be x is negative 1 and y is positive 10. Let's do another substitution example. In this example, x is equal to 6 minus 3y is a great equation to choose since x is already isolated by itself. So if I take 6 minus 3y, I'm going to use that quantity and substitute it in for x into my first equation. So I'll write what I have, 9y plus 3 times the quantity of 6 minus 3y, that is equal to 18. So first I'll distribute that 3 that's in front of the quantity. 9y plus 3 times 6, which is 18, minus 9y, because 3 times negative 3 is negative 9, is equal to 18. So as I go to combine like terms, I notice that I have a positive 9y minus 9y. So positive 9y minus 9y is going to be 0, so those are going to cancel out. I'm left with 18 is equal to 18. When my variables cancel out and I have an equation that is always true, 18 is equal to 18, this is called infinitely many solutions. This would occur graphically when you graph these two equations and they end up being the same exact line. Every single point on that line would be a solution to this equation. Now let's move on to elimination. The goal of elimination is to identify a variable to eliminate so that you can eliminate one variable, you're left with the other, so then you can plug that first variable in and solve for the second. So as I can see, I have 2x minus y is equal to negative 1, and 3x plus 2y is equal to negative 1. I want to identify which variable is going to be easiest to eliminate. I can see that I have a minus y in the first equation and a plus 2y in the second equation. Since those equations are already opposite signs, a minus y and a plus 2y, that's going to be easier for me to eliminate because those will zero out when I add them from top to bottom. The only thing that my top equation needs is my top equation needs a coefficient of positive 2. So I'm going to multiply the entire equation by positive 2. So when I rewrite my equation, multiplying every coefficient by 2, I am left with 4x minus 2y is equal to negative 2. I'll stack my second equation right below it just as it was. 3x plus 2y is equal to negative 1. Now when using elimination, we are going to add our equations from going down, and when we add our equations, one of our variables will cancel out. In this case, 4x plus 3x does not cancel. That will be 7x. What cancels are the y's, just like we set it up for. Minus 2y plus 2y cancels out to 0. So we are left with 7x is equal to negative 2 plus negative 1, which is negative 3. I'm almost done solving for x. I just need to divide by 7 on both sides. So x is equal to negative 3/7. Now that I have one of my variables, negative 3/7, I can substitute negative 3/7 in for x into one of my original equations. It doesn't matter which one. So I'm going to choose the first one, and I am substituting negative 3/7 in where x was originally. So 2 times negative 3/7 minus y equals negative 1. I need to multiply this 2 times negative 3/7, so to make this a little easier, I wrote 2 as a fraction over 1 and drew arrows to show that I can multiply straight across. Negative 6 over positive 7 minus y is equal to negative 1. Finally, I need to isolate y, so I'm going to add 6/7 from the left-hand side, cancel it out, and add it to the right-hand side. Negative y is equal to negative 7/7 over 6/7. I just changed this negative 1 into a negative 7 over 7 to make it easier to add because I need common denominators. So negative 7/7 plus 6/7 is negative 1/7. Divide by negative 1 to fully isolate y, and y is equal to positive 1/7. Finally, I can write my solution as an ordered pair because if we were to graph these two lines would intersect at the ordered pair negative 3/7, 1/7. Let's do one last elimination example. I have 3x minus 8y is equal to 24 and negative 12x plus 32y is equal to 96. So which variable is going to be easiest to eliminate? Well, either way, I could eliminate the x's because I know that 3, if I multiply by 4, will give me 12. I can also see that I can easily multiply 8 by 4 to give me 32. So I'm just going to choose the x's since I'm working with smaller numbers there. So I'm going to take my first equation and I'm going to multiply my first equation by positive 4. 3 times positive 4 would be 12x, minus 8 times positive 4 would be negative 32y, and 24 times 4 is 96. I'll stack my second equation right below it because now I can go ahead and add. So when I'm adding straight down, 12 minus 12x is 0. Negative 32 plus 32 is also 0, so that means for my left-hand side, I'm just left with 0. I add 96 plus 96, and that equals 192. Well, this is interesting because we canceled out our variables, but we do know that 0 is not equal to 192. This means that there is no solution to this system. In a graphical sense, this would mean that these two lines would be parallel to one another, which means that they would never intersect. Now you try and solve some systems problems on your own. You can use either method, substitution or elimination. Make sure that you write down any questions that you have and you check your answers with the answers on the right-hand side of the page. We'll go over any questions that you have in class tomorrow. See you tomorrow.